A comprehensive guide to computer processors, CPUs. A processor, or central processing unit, CPU, is often called the brain of the computer because it carries out most of the computing tasks and controls the operation of other components in the system. A CPU interprets and executes instructions from programs, enabling a computer to perform tasks like calculations, data manipulation, and system control. Here's a more comprehensive breakdown of computer processors. 1. What is a processor? CPU. Definition. A processor, or CPU, is an integrated circuit, IC, responsible for interpreting and executing instructions from computer programs. It performs the essential tasks needed for the functioning of software applications and operating systems. Key roles of a CPU. 1. Fetch, retrieve an instruction from memory. 2. Decode, translate the instruction into a form the CPU can understand. 3. Execute, perform the operation specified by the instruction, e.g., arithmetic calculation, data movement. 2nd, components of a CPU. A. Control unit, CU. The control unit coordinates and directs the operation of the processor, managing the flow of data between the CPU and other components like memory and input-output devices. It sends signals to the arithmetic logic unit, ALU, to perform operations, and to memory for reading-writing data, B. Arithmetic logic unit, ALU. The ALU is the part of the CPU responsible for performing arithmetic, addition, subtraction, etc., and logical and or not operations. It's essential for computations that drive most software processes. C. Registers. Registers are small, fast storage locations within the CPU that hold data temporarily during processing. Some common types of registers include accumulator, holds intermediate results during operations. Program counter, PC, points to the next instruction to be fetched. Instruction register, IR, holds the instruction currently being executed. D. Cache. The cache is a small, high-speed memory located within or near the CPU, designed to store frequently accessed data or instructions. There are typically multiple levels. L1, cache, directly on the processor chip, very fast but small. L2, cache, larger than L1, may be on or near the CPU. L3, cache, even larger, typically shared by all cores on multi-core processors. 3. How processors work. The basic operation of a CPU follows the fetch, decode, execute cycle. 1. Fetch. The CPU fetches the next instruction from memory, RAM. 2. Decode. The control unit decodes the instruction and prepares the necessary components to carry it out. 3. Execute. The ALU performs the arithmetic or logical operation, or the processor carries out the command, such as moving data to a register or memory. This cycle repeats rapidly, typically billions of times per second, depending on the clock speed of the processor. 4th, key features of modern processors. A. Clock speed, frequency. Clock speed, measured in hertz, indicates how many cycles a processor can perform per second. Modern CPUs operate in gigahertz, meaning billions of cycles per second. A 3.0 GHz CPU can theoretically perform 3 billion cycles per second. Higher clock speeds generally result in faster processing, but other factors like architecture and the number of cores also play a significant role in performance. B. Number of cores. A core is an individual processing unit within the CPU. Modern processors are multi-core, which allows them to handle multiple tasks simultaneously, increasing performance in multi-threaded applications. Dual-core, 2 cores, quad-core, 4 cores, hexacore, 6 cores, octa-core, 8 cores, deca-core, 10 cores. C. Threads and hyper-threading. A thread is a single sequence of instructions that a processor can execute. Hyperthreading is a technology developed by Intel that allows a single physical core to execute multiple threads simultaneously, essentially allowing the CPU to perform two tasks at once per core. Single-threaded performance refers to how fast a CPU can process a single task. Multi-threaded performance refers to how effectively a CPU handles multiple tasks or threads at once. D. Instruction Set Architecture, ISA. The instruction set architecture, ISA, defines the set of instructions that the CPU can understand and execute. Popular ISAs include x86, developed by Intel and widely used in desktop and laptop processors. ARM, a more power-efficient ISA, commonly used in mobile devices, tablets, and some laptops. E. Cache size. Larger cache sizes allow for more data to be stored closer to the processor, which reduces the need to fetch data from slower main memory. RAM. This improves performance. L1, cache, small but very fast. L2, cache, larger, slightly slower than L1. L3 cache, even larger, shared among all cores. F. Thermal design power, TDP. TDP represents the amount of heat a CPU generates under maximum load and helps determine the cooling requirements for the system. 5. Types of processors. A. Desktop processors, Intel Core Series, i3, i5, i7, i9. Offers a range of performance levels, with higher numbered models providing more cores, cache, and higher clock speeds. AMD Ryzen competes directly with Intel, offering multi-core performance and strong value for the price. Example: Intel i7-1370K. 8 performance cores, 8 efficiency cores, 16 threads, 3.4 GHz base clock, 5.4 GHz turbo boost, 125 watts TDP-B. Laptop processors, Intel Core i5/II7, U-Series, P-Series. These are optimized for lower power consumption to prolong battery life while still providing strong performance. AMD Ryzen Mobile, a competitive choice offering energy-efficient, multi-core performance. Example: Intel Core i7-1165G7. 4 cores, 8 threads, 2.8 GHz base, 4.7 GHz turbo, 15 watts TDP, low power consumption. C. Server processors. Server processors are optimized for high performance, multi-threaded applications, and high reliability. Intel Xeon, high-end processors for servers with large numbers of cores, high memory bandwidth, and support for virtualization. AMD EPYC, a competitor to Intel Xeon with a focus on price-to-performance ratio and scalability. Example: AMD EPYC 7742, 64 cores, 128 threads, 2.25 GHz base clock, 3.4 GHz boost clock, 225 watts TDP-D. Mobile processors, smartphones, tablets. Qualcomm Snapdragon, a popular mobile processor based on ARM architecture, used in many Android smartphones. Apple A series, Apple's proprietary processors, A14, A15, etc., used in iPhones, iPads, and other Apple devices. Samsung Exynos, Samsung's ARM-based processors used in its smartphones. 6th, CPU performance and benchmarking. A. CPU benchmarks. To measure and compare the performance of different processors, various benchmarking tools are used. Popular benchmarking software includes Cinebench, a widely used benchmark for testing CPU performance in rendering tasks. Geekbench measures both single-core and multi-core performance across different platforms. Passmark, another benchmark for CPU and system performance. B. Single-core versus multi-core performance. Single-core performance important for applications and games that do not utilize multiple cores. Multi-core performance, crucial for tasks like video editing, 3D rendering, and multi-threaded applications where tasks can be split across multiple cores. 7. CPU manufacturing process. The performance and efficiency of a processor are heavily influenced by its manufacturing process. This process refers to the size of the transistors on the chip, which are measured in nanometers, NEM. 7 nanometers, 5 nanometers, 3 nanometers technology. Smaller transistor sizes mean more transistors can fit on a chip, leading to better performance, lower power consumption, and more efficiency. Intel versus TSMC. Intel has traditionally been a leader in manufacturing, but companies like TSMC have also become significant players, producing chips for companies like Apple and AMD. 8. Future of CPUs, quantum computing. Quantum processors use principles of quantum mechanics to perform computations at unprecedented speeds. Though still in its infancy, quantum computing promises to revolutionize processing power for specific types of problems, such as cryptography and materials science. ARM architecture. ARM-based processors are growing in popularity, especially for low-power devices like smartphones, laptops, and embedded systems. Apple has transitioned its MacBook lineup to Apple Silicon M1, M2, a custom ARM-based processor that shows impressive power efficiency and performance. Conclusion. A computer processor is a highly complex component that drives the performance of your computer system. Its architecture, number of cores, clock speed, and other features like cache, thermal design, power TDP, and instruction set determine how fast and efficient your machine performs. By understanding these components and how they interact, you can make better decisions when selecting a processor for different tasks, whether it's gaming, content creation, software development, or general-purpose use.